and we'll get stuff handed out then. We're under stress, so let's talk about stress. So far we've been talking only about strain or kinematics. And stress is the driver for strain. And stress is related to forces that drive the deformation. But it's important to know that stress is not force. And I'll get to that as we go along. Stress produces strain. And there is the description, or the mathematical description of the dynamics of deformation is that stress is proportional to strain through some quantity that we'll talk about here called rheology. But it's also important to recognize that this term strain and this proportionality, or this functional relationship that describes rheology, is not quite the strain that we've been talking about. Remember I said strain is a weird, complicated property? Because what we've been talking about is what's called finite strain, which is purely geometric. And it's a general description of distortion. This relationship between stress and strain, or that functional relationship, is really the time-integrated effect of small strains, or incremental. So if you want to think about it in terms of calculus, it would be the integration of a functional relationship between stress and strain integrated over time would yield finite strain. You don't want to think about that problem. So like a line integral and a bunch of weird things like that, but you don't even want to, and it's like 9 equations, but don't worry about it.
3 pages.
It's ugly, in other words. But the important point is that that can be dealt with. That's a classic problem that people these days do numerical modeling problems that use that basic relationship. And so you can model a geologic process by knowing a functional relationship via rheology, and you can calculate effects. Whether it's right or wrong, it's still a model. But to do that, we got to get to there. We got to first talk about what stress is, dude. Because if it's related to strain, or this incremental strain quantity, what is it? Well, to get to that point, the first thing you want to talk about is a concept that engineers often refer to as static equilibrium. One of the nice things about geologic processes is they're so slow that we never have to worry about terms like inertia or kinetic energy or any of that kind of stuff. But for all intents and purposes, they're Zippo. They don't count. I mean, what's the momentum of a plate, right? I remember thinking about this when I was a student. Oh man, it must be this gigantic quantity because it's such a large mass. Well, it is a large mass, but the velocity term is so slow, the momentum of a plate is about like a schnauzer chasing his tail. So it's not a big thing to worry about. At any rate, so let's talk about force as mass times acceleration, right? And that's a vector quantity. An important thing about if you apply a force or a load to a material, there's sort of two outcomes. One of them is a dynamic outcome in which the material moves or accelerates. That's force mass times acceleration. But alternatively, if you apply a load, it can just sit there like a lump, which it is, or whatever. In the second case, there's still a force. There's something just sitting there. There are actually still forces applied to it. The chair sitting there, or me standing here. I am under the force of gravity. But you have to ask them, if force is mass times acceleration, that's always bugged me, right? So how does that work? Well, the real answer is Newton's third law. Because for every force, there's an equal and opposite reaction, right? So in that particular case, another way of thinking about Newton's third law is related to a rheological property, or a relationship between motion and force that is called elastic behavior. And elastic behavior is the classic behavior of a spring. And it's often characterized by Hooke's law. If you're into geophysics, you'll know Hooke's law backwards and forwards, because Hooke's law is completely related to seismology. Seismologists work with Hooke's law all the time. And all Hooke's law is, in one dimension, is you do these little lame experiments, probably in physics labs, where you show that force is directly proportional to displacement on a spring. Or you can make a graph with force on one axis and displacement on the other axis, and that's a linear relationship. And that the proportionality constant is sometimes called the elastic constant, or specifically it's actually referred to as Young's modulus. And the elastic modulus is simply a measure of the strength or the rigidity of a material in the context of elasticity, right? So if a material is wimpy, like the little rubber band I got in my hand here, only a small force will produce a large displacement. So the slope of the line is low for a material that has low rigidity. If this was a spring that was, like a massive coil spring or something like that, and I started pulling on that, I would have a lot more difficulty pulling that equal amount for the same amount of displacement, or like the thing that's illustrated here. So the slope of that line would be much greater in that particular context. So some materials are more rigid than others, and that's just a characteristic. That's a physical constant called the elastic constant. I guess I had a question here. I just went through it instead of running through the question, but you got the basic idea. Now it's important to realize that all solids display some form of elastic behavior. It's what allows me to keep from falling through the floor, right? And it's actually, one way to think of it, that is a restatement of Newton's third law in a sense, because what's keeping me from falling through the floor is the material that I'm standing on has an elastic response to the force that I apply to the floor, and it pushes back with an equal and opposite force. So I'm actually producing a small deformation on the floor as I walk around, and that's the material pushing back at me. The physical reason for elastic behavior in materials is really to do with chemical bonding in the solid, such that you can compress the bonds or stretch the bonds. And if you take them a small amount, that amount is just a trivial amount of motion within the solid. An important thing about, I don't know if I said it here, the important thing about elastic behavior is that if I remove the force, it always is recoverable. The spring, I think I probably supposed to say it on the last slide. If you pull on the spring and release it, it comes back to where it started. And that's the critical part about elastic behavior, is that it's non-permanent deformation. So any elastic behavior in the geologic record, in a sense, is gone, right? It's just ephemeral. You can apply a load to a material, but it responds to that. But it's related to the material and the stresses and the things like that that occur within the body. Or I guess I'd have, next slide. Properties of elasticity. The two important properties is that it's entirely recoverable. You remove the force and it comes back. The other is that there's a linear relationship between force and displacement, which is about the most easy quantity to characterize if it's a linear relationship. Another type of behavior, this is an important one to think about a material behavior, is what's called viscous behavior. And viscous behavior is often thought about in the context, if you ever played with a shock absorber, there's a good illustration of this. Go to Midas and they have the broken shock absorber, right? You can play with. But what's the basic physical property of a fluid is the sense that if you take that shock absorber and you pull on it on one end or push on it, whichever way you want to do it, it'll always move if you pull on it at all. But the harder you pull on it, the faster it moves. That's basically the physical property of fluid behavior. Or a way that's often quantified is that the force that you apply to that end of that device is directly proportional to the velocity. So if you don't pull on it at all, it just sits there. If you pull on a little bit, it moves real slowly. And the harder you pull on it, the faster it moves. And if that relationship is linear, it's called linear viscous behavior. And or alternative, so that the force is proportional to velocity. But remember, the velocity is the time derivative of the displacement, or it's the rate of displacement, or meters per second, or whatever you want to call it, right? So this quantified that there's a proportionality constant where force is directly proportional to velocity, and that proportionality constant is a constant called the viscosity. The viscosity is the flow equivalent of the rigidity in elasticity. So a low viscosity means if you have a diagram that makes a plot of force versus velocity is analogous to the elastic plot where you have force versus displacement. But this is force versus displacement rate. So if you have a very low viscosity, you have a very low slope. A small change in force will make it move much, much faster. If it's a high viscosity, it takes a larger change in force to produce an equivalent change in velocity. That's not rocket science, it just makes sense. Think of it as being water and honey or something like that, right? How much force you would have to push on it. If you were swimming in honey, it would be a lot harder than swimming in water, right? Or swimming in the air, right? The air is a fluid. And it has a very different response than swimming in water, right? We swim in air all the time. This is a 1D equivalent of, in the sense of force, and this is proportional to that relationship. What did I forget here? This is called Newtonian viscous behavior. And there's some odd physical properties that are associated properties of Newtonian viscous flow. And one of the most important ones is that material distortions are not recoverable without a reapplication of forces. And I want to show you this video just for fun while it's going. I'm not be saying he's going to come back to it. The material also has no inherent strength, so that curve projects back to zero. So one way of thinking of that is in a perfect fluid, if you pour it onto the floor, it will spread out under gravity to one atomic layer thick, if it was a true perfect fluid. Now, real fluids have surface tension and things like that. But for all intents and purposes, close enough for government work for most fluids, right? And the air is probably the closest to a true Newtonian fluid. The material behavior is that the force required to produce the deformation produces a rate-dependent effect. So you have to think time instead of think about just apply a force, something happens. In the case of fluid behavior, the larger the force, the faster the material flows. Or alternatively, if rate is a constant process, you'll be at fixed force relationships in the fluid. So if it's flowing at constant velocity, then there's a constant forces within the material that make it work that way. And the odd thing about materials that have fluid behavior is estimates for geologic processes suggest that the range for viscosities for earth materials is about 30 orders of magnitude, which is rather phenomenal, actually. That includes water, but if you call that a geologic material, but it's still, you'll do water, I guess, with Langford. It's a fluid flow problem. But even within earth materials, solid earth materials, the range of estimates for viscosity is extremely large. I'm going to go just for fun, just to show you this. Whoops.